In this module, we're going to talk about standard enthalpies of formation and what really is an extension of Hess's law. Alright, so first of all, some definitions, which these definitions in particular are really good to memorize. The standard enthalpy of formation, that's what this symbol right here means. Change in enthalpy for F is formation, and this superscript lowercase o stands for what we call standard states. And that's just a change in enthalpy when you form 1 mole of a compound from its constituent elements in their standard states. What does that mean? Well, a standard state is just the state that a substance is in when it's its most stable state under standard conditions. Standard conditions are just 25 Celsius and 1 atmosphere, room temperature and pressure. So whatever the compound is, we could do, for example, sodium chloride. Let's look at that. So we could write down the chemical equation for the delta H of formation of sodium chloride. It would just be, okay, so let's start at the right hand side. Sodium chloride is NaCl, right? And it's a solid under standard conditions, 25 Celsius and 1 atmosphere. So what elements make up sodium chloride? Well, sodium and chlorine. What do you think the standard state for sodium is? At 25 Celsius, 1 atmosphere, sodium's a metal. It's going to be a solid, right? And chlorine, its standard state is Cl2 gas. Remember Hofbrinkel, the diatomics? Now this has to be balanced. So, let's move these guys. Remember, it's for 1 mole of the substance, so you balance it on the left-hand side. This equation right here describes the heat of formation of sodium chloride. Whatever the delta H is for that, that's it. And here, this is also really good to remember. If you forget this, it's really going to mess with you, like on a test. The heat of formation, the enthalpy of formation for any element in standard state is defined as being 0. So the heat of formation of sodium is 0, heat of formation of chlorine 0 when it's gas, so on. All right. Now, here's where we really get into how we, as a practical matter, use Hess's law most of the time. You can look up the heat of formation for almost any compound. So if you have a chemical reaction that you're looking at and you want to calculate the heat of reaction for that, if you look up the heats of formation of the products and the reactants, you can calculate the heat of formation real easily, simply, for that reaction. So let's look at our generic chemical equation. AA plus BB goes to CC plus DT. Just remember the lowercase letters are the coefficients, and the capital letters are the compounds. Right? So this is good to memorize. This is the form of Hess's law that you use most often. The heat of reaction, the delta H of reaction, it's equal to the coefficient of each product times its heat of formation. Add all those up for the products minus the coefficient of each reactant times its heat of formation. So let's use this. So given this following information, we want to calculate heat of reaction for the decomposition of ammonium chloride into ammonia gas and hydrogen chloride gas. We want to calculate delta H of reaction. And you can look up in tables anywhere. In the back of your textbook, whatever textbook you're using, there's going to be some of these there. So the heat of formation of hydrogen chloride gas is negative 92.3 kilojoules. Oh, by the way, this is important. The state matters. The heat of formation of aqueous hydrogen chloride or hydrochloric acid is going to be different than hydrogen chloride gas. Ammonia liquid has a different heat of formation than ammonia gas, and so on. So anyway, given these heats of formation, we want to calculate the delta H of reaction for this. So we just do products minus reactants. So the two products are ammonia and hydrogen chloride gas right here. And this 1 here is just to show you that even though the coefficients are 1, it doesn't change anything. If they weren't 1, whatever the coefficient was here, well, we'd have to multiply it by the heat of formation of ammonia and then hydrogen chloride and so on. Minus 1 mole of ammonium chloride, this here, times the heat of formation of ammonium chloride. Add those up and we get 176.8 kilojoules.